So today's video is brought to you by the Lego Viking Blacksmith. Nice little hammer here for work. And it seems quite happy to be making things. So let's do it. Remember, we were looking at compound interest, and we had just discovered the compounded annually formula, which was A equals some principal times 1, which represented 100% of the deposited value, plus the interest rate. Remember, we're always converting that to a decimal, raised to whatever the time period was. For simple interest back from lesson 3.1, we were looking at, we really had three different versions. The one that looks the most similar to the exponential one was this principal times 1 plus the rate times the time. I don't tend to use that one as much. I prefer the P plus the PRT version. Either way, we're going to smash all of this in Desmos, because Desmos will very quickly create this table and then create this graph. In fact, it'll do it simultaneously. So notice we're given $600 for our initial investment. That's our principal. We're investing it at a rate of 5% interest, simple interest, or compounded annually, and we're going to try to compare those two values. So scamper over to Desmos, and what I'm going to do is I'm going to type these into the table as an equation in the table. So right here I've selected the y1, and that's going to be my p times 1 plus r to the t. I'm going to type that right in there. So 600, that's my principal, times 1 plus the 0.05, that was my rate. And I'm going to raise that to the t value. Well, if I want to use t, I have to tell Desmos that my x is my t. So I change the x1 to t, and then I'm going to put the raise that to the t value here. Now I can put in my 10 years, my 20 years, my 30 years, and my 40 years, and these are the respective account balances after each of these amounts of time. Let's compare that to the simple interest. That was the 600 plus 600 times 0.05 times t. And now we can see the difference between these two values. And there's another way we can do this. If you recall function notation from back in Unit 2, we could type out an equation, say like f of x. I'll make that my exponential one. Oops. And I'll use g of x for my simple interest version. And then I'm going to create a second table. Oops, that was not a table. There we go. And for here, I'm going to put in f of x1, g of x1, and I'm just going to regenerate the exact same table. And I'm going to tell you why I'm doing this in just a second. So now if I want to see how much more money did I make by the compound interest, I can type in the table, take the f of x1 values and subtract from them the g of x1 values. And there's my difference. So after 10 years, the compound interest earns $77 more. After 20 years, it earns $391 more, and so on and so forth. I think that's just a really nice, handy way to compare the difference between the two values. Now, we were supposed to look at a graph. So if we hit our zoom fit on any one of these tables, we can now get this nice picture of the graph. And you can see that the exponential here in red is just, we got this nice separation between the linear, or the simple interest and the compound interest. And looking at 45 years here, I could draw in x equals 45. Here's that big difference between the two. And as time progresses, this distance gets more and more pronounced, to where if we look at, say, 1,000 years later, of course we're all dead, but whatever, it's an insane amount of money that the compound interest makes compared to the linear interest, or the simple interest. In fact, the simple interest almost didn't make anything 1,000 years later.